Okay, so we have a baseball player who's going to steal second base. The first baseman sees him move and throws the ball at 25 meters per second due north to second base. All right, so I'm just going to write down, this is obviously a multi-part question. So in part one, okay, we know that the velocity, so that's V with the arrow over top, is 25 meters per second north, okay? And that takes 2 seconds to get there. While the ball is in the air, the player changes direction in an attempt to return to first. The ball is instantaneously caught and thrown, so there's no, because it just makes it really difficult if we're taking into account the time it takes for the person to catch it and then return it. So we're just assuming it kind of bounced off of him instantaneously back. Okay, so they throw it at 22 meters per second, a distance of 30 meters. Okay, so part two, since he's throwing it back to first base, then that velocity is which direction? South. It doesn't outright say that, but it does say he throws it back. All right, so that means opposite direction. And that is a distance of 30 meters. But we'll say it's a displacement of 30 meters south. Yeah. Okay. What's the displacement of the ball, and how long is the ball in the air? What's the average velocity of the ball? Okay, so first off, can I find the displacement for part one? Yes, I just have to manipulate for D. Okay, so D is going to equal V times T, so that'll be 25 times 2, which is 50 meters. Okay, 50 meters north. Everybody okay with that? Okay. We already know the displacement for part 2, so now we can figure out the total displacement. Okay, so the total displacement is that it went 50 meters north and then 30 meters south, so the displacement is 20 meters north, right? Because if you've ever watched somebody caught in a rundown, okay, that's where they're chasing them back and forth, they always get closer and closer together to trap them, right? And then they can tag them out, right? Because the runner can't leave the baseline. Otherwise, baseball would be far more interesting, okay? But if you leave the baseline while running, you're out automatically, right? Because otherwise, you know, you could just run around the field until you got back to the base anywhere you wanted. And I guess maybe that would be less interesting. I think it'd be more interesting. Okay, so we got 20 meters north as our total displacement. Okay, the next thing it asks is, how long is the ball in the air? Well, I know for the first part, it's in the air for 2 seconds, but I don't know how long it's in the air for the second part. Can I figure it out? Yes. Okay, so T equals D over V. Okay, so we've manipulated for T instead. Okay, so that'll be 30 meters over 22 meters per second. Okay, so 1.36 seconds. Okay, so that means that our total time is going to be 3.36 seconds. Okay, everybody with me there? Okay. Now, the next thing is, what's the average velocity of the ball? Well, average velocity is total displacement over total time. Okay, so oftentimes when you run into a question that has more than one part, you basically need to find V, D, and T for all of them. Okay, well, at least D and T for sure, and then put that into a total, right? Then you can deal with the whole trip after that. V average is average velocity. It's the same thing. Yes, this is, yes, sorry. Because I wrote it in the total, I didn't write VAV. Yeah, okay, so yes, this is V average. Okay, so we'd have our 20 meters divided by 3.36 seconds. Okay, and that would give us our 6 meters per second. Okay, everybody all right with that one? Any other ones on there giving us trouble? Number 4? The canoeing? This one? The bus? Okay. Okay, so we have the bus travels 11 kilometers with an average velocity of 21. So that's telling us just the average velocity for part 1. Okay, so not to be confused, because I think the average velocity thing is confusing people a little bit. Okay, so if it's at average velocity over the whole trip, that would be something else. Okay, so in part 1, Okay, we know that the displacement of the bus, sorry, it says velocity, but there's no directions in this question. You know why? Because this used to be a vector question, and I changed it without changing all the stuff I should have changed. That would definitely be confusing. Okay, so 11 kilometers has to be a distance because there's no what? There's no direction. This can't be a velocity because it has no direction. Okay, then travels 1 kilometer at a smaller, sorry, this used to be a vector question and I changed it. Okay, does it make more sense now? Okay, yeah, because mathematically it isn't difficult once you realize all the velocities should say speed. Yeah? Do I need to go through the whole thing or are we good now? Good now? Okay, sorry about that, guys. Okay, any other ones? Okay, so with number 12, we have a 60-kilometer trip. That's how long the whole trip is 60 kilometers. So I'm going to go over here and start with my total information. Okay, so it's 60 kilometers. That's a distance. Okay, and it says average velocity again. Oh, no, sorry. That's the displacement. Okay, 60 kilometers north. Okay, and it travels with an average velocity of 40 kilometers per hour in the direction due north. Okay, the trip consists of 3 parts. All right, so there's what we know about the total. What can I find about the total right now? Time. That's probably a good idea to have the time for the whole trip as well. Okay, so if I do that and I go d over v, I'm going to find that the whole trip takes 1.5 hours. Okay, everyone okay with that? All right, now we'll start putting together the pieces of this trip. Because what they're going to want is how fast was it going in part 3, right? Okay. So in part 1, we have a constant velocity of 25 kilometers per hour north. Okay, and it's 15 kilometers. Does the north really matter in this question? It does, except that I have to have north on my answer. Everything is north, right? So I could really do this like a distance and speed question if I wanted to, because the object's not changing direction. Okay, in part 2, we're looking at 62 kilometers per hour for a velocity, and that's again north, right? For the next 32 kilometers. Okay, and what velocity does it travel for the last 13 kilometers? Okay, all right. If I want to find the velocity in part 3, what else do I need? Time. Okay, so that's what I've got to work towards. I know the whole trip takes 1.5 hours. Can I find out how long these 2 parts take? Yes. Okay, so t equals d over v. Okay, so we'll have our 15 kilometers over 25, and that comes out to a point. They're punching it. 15. Okay, so 0.6. So this is 0.6 hours. Okay, and I got to do the same thing here. T equals d over v. So that'll be 32 over 62. Okay, so 0.516 hours. And again, you should keep all of your decimals there, just like we have in the past, 0.516. All right, so can I figure out how long part 3 is now? Because I know the total and I know the other 2 parts of the trip. Okay, so I'm just going to take those numbers, so plus 0.6, that'll, okay, and then go 1.5 minus that. Now I have the time for part 3, which is 0.3838, whatever. Okay, so 0.3838, not seconds, hours. Now I can find the speed in the last part, or sorry, the velocity in the last part. Okay, 13 kilometers, okay, divided by that 0.3838. Okay, should give us our 34 kilometers per hour north. Is that all right? Okay, so that's a little bit tricky. Basically, though, all it is I ask you to do the same manipulation of v equals d over t 3 times so you get good at it. Yeah. I did just to be fast. In the end, that's what I want to see. As like if I'm giving you marks, that's a mark showing me the manipulated form. You do it in your head, do it in your head. Okay. No, you don't have to show yourself crossing off I just always walk through that. Well, except for this time, always walk through that. When we start getting to more complex equations, you'll probably show all of that, just because the equations are a little more heavy. Yeah. Okay. Any others? Okay, that's good. I'm glad you guys asked about that. Okay. Okay. So the big thing with slope calculations is that there's kind of two ways to calculate slope. There's rise over run, and there's y equals mx plus b. They're actually the same thing. Okay, it's two different sides of the same coin. The benefit of using y equals mx plus b is that it can tell you more things. Okay, rise over run will get you the slope, and that's it. Okay, that's all it'll be good for. Once you have the slope, then it's done. Okay, whereas y equals mx plus b allows you to find values that are not on the graph. Okay, it's what we call extrapolating. I think I used that term in the other podcast. It allows us to extrapolate, that is, find stuff that's not on the graph. It may not have been in the experiment, but we can use the data from the experiment to figure stuff out and apply it to other things, or apply it beyond, which is usually what we do with experimental data, because you can't run everything in a single experiment, so you sometimes have to extrapolate. Okay, so what we're looking at here with the position versus time graph is that the slope of this graph is actually v equals d over t. Okay, and here's why it is. Okay, if I have my graphing equation, y equals mx plus b, okay, so let's say that this line just continues on and actually has a y-intercept, a b, okay? What we're saying here is that my y values are positions, okay, because position is on the y-axis, okay? And my x values are time, because time is on the x-axis. Everybody all right with that? So if I manipulate for slope, which is m, what I'm going to do is subtract b over to this side, right? We looked at this before, y minus b over x equals m. Okay, everyone okay with that manipulation? On this graph, here's what that's saying. Final position minus initial position over time. Okay, because my initial position is right here, b. It's where I was when the time was 0, right? So at the beginning of the experiment, this is where I was. Okay, at the end of the experiment, we'll just say I was up here. Okay, well, that's my final position. And final position minus initial position solves for displacement, right? PF minus PI. I talked about that the first day. Okay, final position minus initial position equals displacement. Okay, so by finding my change in position, that's what D is, okay? My change in position is displacement. By finding my change in position and dividing it by the time, I get velocity. Okay, that's where the formula V equals D over T comes from. It's the slope of a line on a position time graph. Okay. Yes, you will also have to calculate them for velocity versus time graphs. The good news is it's the same method. You're just going to get a different value. Instead of getting velocity, you would get acceleration. Okay? And it's the same for any graph. Whatever the slope is whatever the change in this is over the change in that is. Okay, that could be if you were graphing, the value of, I don't know, let's say you've got bought shares in Bombardier, okay, which is that plane company in Quebec that loses money every year. Okay, so your graph of their share value would look like this: dollars over time. Okay, yeah, and so the slope of that line would be the amount of dollars you lose every day. Okay, by having shares in that company. You shouldn't buy shares in a company that's losing money, incidentally. Okay, now that's your first lesson. That's stock market 101. Okay, don't buy shares in a company that's going under. All right, because they won't be worth as much when you sell them, and that's bad. Okay, like if I could go back 30 years, this is why I want a time machine. Okay, and buy shares in Google, who was a nobody when I started teaching, I wouldn't be teaching now. But I didn't. Okay, so yeah, that's That's kind of how that works. There you go. So graphing is important in all kinds of things, even in money. All right. So if we're looking at this position versus time graph here, obviously this is a position versus time graph of an object that's moving around. Agreed? Right? Because its position is changing, at least in many parts of the graph. In what parts of the graph is its position not changing? Right, B and D. So in other words, in those places, the object's doing what? Standing still. Right. Okay. So in part A here, I'm going from position 0 to position 6 meters, positive 6 meters. Okay. What kind of motion is that? Okay, it's positive. And is it uniform? I mean by that it goes up by the same amount every time. Yes. Okay. Each second, like if there was a 1 on here, right? The 1 and the 2, the triangles would look the same. Okay. So this is an object that's traveling at a constant velocity in a forward direction. Right. So we might want to make a note of that. Okay. This one's in your notes package, right? Yeah. Okay. And then we said in B that the object is standing still. Okay. And the reason for that is that the line's has no slope, right? The position's not changing. He's at 6 meters at the beginning of B. He's at 6 meters at the end of B. He hasn't gone anywhere. Now, since this is flat, its slope is, which should make sense. If you're standing still, what's your velocity? 0. Okay, it's a flat line, should have a slope of 0. Okay, in part C, what's the object doing? Well, it's not decreasing speed. It's going backwards at a constant velocity. Yeah, constant. We said backwards. We gave it direction. Right. That's where we really gotta keep those ones straight in our head. This is an object going backwards. Good question. We'll look at that in a minute. Okay, so this is an object going backwards at a constant velocity. Okay, how do I know it's going backwards at a constant velocity? Because his position goes from positive 6 to negative 10. Okay, the only way for me to end up behind where I started is to go back. Okay, now, good question was asked, is he going faster here than here? All right, let's look at that. Can I calculate how fast he was going in A? Yeah, okay, in 2 seconds, he went 6 meters. All right, so V equals d over t. Essentially, I'm calculating the slope of that part of the graph. Okay, so 6 over 2 is 3 meters per second. And that would be positive because it was forwards. Okay. In part C, what's my displacement in part C? Okay, negative 16 meters, right? Because again, we want to go final position minus initial position. So that's negative 10 minus positive 6. So that's negative 16. Okay, so V equals, in that part, negative 16 divided by, and that took him from 6 seconds to 10 seconds. Okay, so it took 4 seconds. That means, yes, he was going faster in that part, but in the opposite direction. Okay, so the magnitude of his velocity was bigger, and the direction was opposite of part A. Yes, that's what the table went up. They just show the numbers without showing you how they arrived at them. So I want to show you how they arrived at those numbers. Okay, and we said in part D already that the object is standing still. Sorry, Andrew. Absolutely. Any declining slope is negative. Yeah. Okay. Part E and part F. How are the motions in part E and part F similar? They're both positive. Yeah. Okay. At least we're moving in a forward direction. Are we at a forward position? No. Okay. We're still behind where we started, but we're moving forward because we're getting closer to where we started. Right? In fact, really all this object is doing is going forward and backward, forward and backward, forward and backward. It just doesn't look that way on the graph because it's showing that motion as a function of time. Okay? Yes. Yeah, the total displacement for this one is 0 because the final position is 0 and the initial position is 0. Okay. And that was actually the next thing I was going to get to. So getting ahead of me. Okay, let's look at how would I calculate the distance, the total distance over the whole trip. Yeah, I got to add up every section. Okay, the displacement we know is 0 because the final position and the initial position are the same. So it didn't end up going anywhere, it ended up back where it started. But it did go forward and backward a whole bunch of times, so it traveled the distance. Okay, so in this first part, we said that it goes from 0 to 6, so that's 6 meters. Okay, so we'll have 6, and then here it went 16. Okay, from in part C here, and then in part D, how far does it go? Doesn't go anywhere. Okay, and then in part E, 6, and then in part F, 4. Did we really have to separate those two, or could we have just gone and went from 10 back to 0? Yeah, okay, plus, we could just go plus 10, right? So the total distance traveled here is 32 meters. All right, can I calculate my average speed now? Yes, okay. We're just for simplicity's sake going to say that it got to 18 seconds, okay, just so we don't have to figure out 17 point whatever that was. All right, so we got a total distance of 32, a total time of 18 seconds. 32 over 18 gives us our average speed over the whole trip. That is a very typical type of question that you could get on a unit exam. Here's a graph, calculate the following things. I would never give you one where you had to interpret. Yeah, because then how do I make a key for that, right? Everybody interprets that a little bit differently. And there is, yes, you could do this if it was just a line graph, right? I could find what's X when Y is 0. Okay, I could do that. But on this graph, because it's not a single line, I can't do that, right? So on a test, I would make sure that they ended at points that you could easily follow over using the grid lines and stuff. All right. Yes, the velocity, the total velocity for this trip is 0. Yeah. Yes, we could. Yes, because it says 4.5, so it was 17.5 up here. Yeah. We just, I don't always, if I give you a graph, I won't always give you this chart, right? Absolutely. Always. Yeah, that's one of those absolutes. Okay, so yes, if the displacement is 0, velocity has to be 0 because V is d over t, and 0 divided by anything is 0. So anytime the displacement is 0, the velocity is 0, always. Yes, vice versa. Okay, I mean, because we're just manipulating the formula, right? If I just go, oh, well, okay, what's d when v is 0? 0, right? Because anything multiplied by 0 is 0. Yes, on the test, either it'll be like on the chem test where you'll be allowed to have the formula sheet I still have to print for you, or I would put them on the front page, one or the other. Probably just let you have your formula sheet. Okay, provided you don't write on the formula sheet the manipulation of every formula on the formula sheet. I have seen that before, and part of this unit is that you can do that on your own, okay, without writing them all down. Okay? And if I see a triangle anywhere on there, oh, man, so help me God. Okay. All right, now instantaneous velocity is something that we just need to talk about. It's not something you're going to often be asked to calculate, okay? But it's important to kind of see how that's done. This graph has curves on it, which is something we haven't dealt with, okay? We looked at a graph a minute ago, okay, that showed like this, it had a bunch of straight sections, and anywhere where the line was straight, the velocity was either constant or 0, all right? So if the graph is curved, the velocity isn't constant, okay? And if the velocity is not constant, that means it's changing. What do we call it when something changes velocity? Acceleration, right? So this graph is showing an object that is accelerating. In fact, this graph is of this. Okay? That's what this graph is of. All right. It's showing in the first part. Sorry, the recording will not pick that up. Okay. So I just threw my marker up in the air and caught it. Okay. Straight up in the air, caught it. All right. So what we have here in this first part is that we see that the rate of change of position is going up, right? The line, because it's a curve, in this part at least, is getting steeper. Okay. Now, so here's how this works. I'm going to explain to you the only thing that I understood in university calculus. It was the first day. I never understood anything after that. Okay. A curve is an infinitely large number of infinitely small straight lines. Okay, so imagine if you look at a curve and it's like looking at a low resolution picture. You can see all the pixels, okay? And because that's how a computer makes curves, right? They just make straight lines. As long as the pixels are really small, you don't notice them, it looks like a curve, okay? So what this curve is an infinitely large number of infinitely small straight lines. Yeah, that's all I understood, okay? So what I need to understand is if I want to find out how fast the object is going at any point on that curve, I need to find the slope of the little tiny line that exists at that point. Okay, now you're probably thinking, okay, how do you do that? Because that's really, really small, right? It doesn't have a b. Okay, how am I going to find an x and a y and all that kind of stuff? Like, how do you find the slope of something you can't even see? The answer is you make it longer. Okay, so what I would do is, if I want to find how fast the object's going at time 7 seconds, where a is, I draw what's called a tangent. Some people have heard of a tangent before. Okay, so it's a straight line that just touches a curve but doesn't cross it. Okay, essentially, it's a line that's parallel to the curve at the point it touches it. So if it's parallel, it has the same slope. Has the same slope, right? If it's parallel to the curve at this point, I draw a line that touches the curve there. I've just drawn a line that has the same slope as the curve at that point, and then I can find its speed. Okay, or instantaneous velocity. So I cheat because you can't put a ruler on a smartboard. Okay, you guys would probably have to do this with a ruler. Okay, this is why you don't actually do it. Right? How do I make a key if everybody has a ruler and everybody draws this line just a little differently? Okay, it's pretty tough. All right, so here's what I do. I draw a line. That's not a very good one, but I can adjust it. That's the beauty of it. Okay, so now my line just touches the curve at that point. Could I calculate the slope of that line? Yeah, I don't know what b is because it's down below the graph, but I could manipulate and find m, and then I would have, if I had a better graph that showed everything, I could find the slope, and that would be how fast it's going at that point. That sounds great. I have no idea what you just said. Sounds great though. Yeah. See, I'm not a math guy. I think I told you guys that. But yeah, no, I know what you're saying. Yes, you could do that. Probably most people haven't learned how to do that yet, which is why I teach it this way. Yeah, right, because that comes later. Okay, so I drew a line, right? And if my graph went actually down to here, I would see where it crosses the y-axis. That would give me b, my y-intercept. Yeah? Then I could pick from, let's say, this point right here where the line crosses this grid line. Okay, I could use that to get y and x. Okay, so I would have y, I would have b because my line would go across here, so I would know what b is, right? I could use those numbers and find out what m is by manipulating y equals mx plus b. Yes. In fact, you're not going to draw any graphs by hand because drawing graphs by hand is, yeah, that went out with like 8 tracks and dodos. Okay, it's gone. Okay, we're gonna learn how to do this in Google Sheets next week. Okay, it'll draw you a line graph and it'll spit out this. It'll say, it'll give you a number. It'll be like 0.515x plus -2. Okay, that's y equals m times x plus b. So Google Sheets will spit that out for you. You have the equation of the line. Yeah? I'm just drawing a line that's long enough for me to get the slope of. Okay, but again, you guys aren't going to have to do this. It's just important you see how it works. Okay, to kind of illustrate that this is an object whose velocity is changing. Okay, again, I'm never going to ask you to do that because it has to be done by hand. You're not going to be able to do that part in Google Sheets.
So, are we ever going to need graphics?
Nope, nope, because yeah, we don't want to do things by hand. That sucks, and it's inaccurate, right? Like drawing a graph by hand is incredibly inaccurate, right? When Google Sheets draws a best fit line for you, it takes into account every single point mathematically. It's got some sort of algorithm that it uses to plot the thing in the right place, same as your graphing calculator would do. Okay, whereas a human being goes, okay, I'm gonna put the ruler on there, and I got the same number of points above and below the line. Looks pretty good. There's my line. I mean, there's a lot of error in that. And there's a lot of judgment in that. Okay, when I used to have to mark graphing questions by hand, what I would do is draw a line I thought was perfect, draw a line I thought was a little bit too steep, a little bit too shallow, and take any slopes that kids calculated between those numbers. Okay, there's a lot of error in that. Okay, and so we don't want to do it that way. Okay, so moving along here to some other stuff to do with this graph. So we said that in this first part, the object is accelerating, okay? And it's accelerating probably right up until this point here. Actually, no, probably right up to this point here. Okay, so it's accelerating because the line's getting steeper, 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 steeper. Now what's it doing once we get to the little red hash mark here? Right, it's starting to slow down because what's happening to the curve? Now instead of getting steeper, it's getting unsteeper, flatter. Flatter, shallower, yeah. Okay, unsteeper. I like that. I don't think I've ever heard that one before. Okay, so eventually, what happens to this object right at point B? Right, it stops for an instant. Okay, not that you could actually observe this instantaneous stop, but it does stop for an instant. How do we know that? Because if I draw a line that's tangent to it at that point, what's its slope? 0. Okay. Yes. No, sorry. It would not stop for longer. It would be in the air for longer. Yes. They only have that instant where, gravity has been slowing them down, slowing them down, slowing them down, and then they stop before turning around to come back down. Yeah? But no matter how high you throw it, that instant is just an instant. Okay? The amount of time it spends in the air is longer the higher you throw it.
They said if you had jumped into a hole the entire center of the earth, by the other side, you would have just enough acceleration compared to the gravity, you would have like an entire second to just step off onto the other side.
Well, I don't know if you'd have an entire second, but I know where they're going with that. Okay, the center of the Earth's mass is obviously pretty close, not exactly at its center because the Earth isn't perfectly round. Okay, and there's continents and land masses. The northern hemisphere actually has a little more mass than the southern because of most of the land mass is there. Okay, but if you were to drill a hole all the way through the center and come out on the other side, and you could fall through it because that's what you would do. Okay, you would fall and increase speed because you'd be accelerating all the way to the center. But then you would pass through the center and start going up the other side. But you'd have all this velocity you gained. Now gravity works against you. But since this distance and this distance are theoretically exactly the same, your velocity here and your velocity here would be identical because your rate of acceleration is the same all the way through. All right, so because everything is the same all the way through, you would get to here and just be able to go, oh, there I am, step out of the hole, and yeah, I'm in China, right, or wherever we come out. Okay. No. No. No is the only answer I have to no, the world is not flat. Okay. All right, so does that make sense there? Okay, and then we see that after that high point, that the object begins accelerating, but now it's accelerating in a negative direction, right? The object is falling. It's in a downward direction. So we see this kind of mirror image curve. Now, obviously, there is one difference here. Okay, the point where I threw it, the position was 0, but I caught it higher up. Okay, apparently 4 meters higher up. So Yeah. So I like threw it in the air and then ran up 4 flights of stairs to catch it. Something like that. Yes. Just know that we don't use the term deceleration in physics. Yeah, because it's a layman's term. So there's only acceleration. Acceleration can be positive or negative. Okay, it's a vector quantity, so we don't use accelerate and decelerate. We just say accelerating backwards, accelerating negatively, something like that.
Like when a graph just ends like that, I was just like a stream goes on and just like stops it.
Well, that's where the experiment ended. Doesn't mean nothing happened after that. We just didn't record anything after that.
Okay.
Yeah.
But like you don't have to like extrapolate it.
Well, from this graph, you couldn't extrapolate. But if I had a line graph, okay, like you guys got showed yesterday, right? Let's say this experiment ended at 10 seconds. I can extrapolate for 20, for a minute, for 2 hours if I want. There's going to be some uncertainty in that because I only ran the experiment for 10 seconds, but I can extrapolate for any value beyond the graph.
If you go back to the graph up there, why does it slow down before it stops?
Catching it.
Well, what if
That's still an acceleration. It's like you go, oh yeah, it stopped. But there is a space of time there, right? It wasn't instant. It looks instant because of our perception of time, but there was a large acceleration there where I stopped it. That's why I feel it when it hits me. Yeah. It can still be a fraction of a second. Just because my scale is in full seconds doesn't mean that things can't happen in fractions of that. Yeah. Okay, any other questions on that graph? All right, so from a position versus time graph, before we get to velocity, okay? So you might want to write this one down. I think we had that talk after the unit exam, right? If I write something down, it's probably important. You should write it down. Yeah. Okay. Position versus time. Okay. We can read off of a position versus time graph, position and time. Right? Because that's what the graph shows. Where is the object at various points in time? So we don't have to do any calculating. We can read that directly off the graph. Okay, we can calculate displacement. And we do that by taking our final position and subtracting our initial position, whatever those final and initial happen to be. They don't have to be the beginning and end of the graph. Okay, I could give you a graph that runs from 0 to 15 seconds and just ask, what's the displacement between 7 and 9 seconds? Okay, so then you would take the position at 9 seconds and subtract the position at 7 seconds, and you would have your displacement between that time. Okay, everybody follow there? All right, other things I can calculate, velocity. Okay, and that will either be the slope of the line, okay, or V equals d over t. Okay? Which one you use depends on what kind of graph you have. Okay? If you have a graph like the one we looked at before that looks like, sorry, I'll come back to this in a second, that looks like this, can you find the slope of that? No. Okay, it's not one single line. You mean you could find the slope of various parts, but okay, for this one you would use like total displacement over total time, so final position minus initial position, right? It doesn't set up to find slope. Okay, but if you had a single line graph, then you would use slope. Yes, and that's what you're doing when you go V equals d over t. You're finding the slope of an imaginary line on the graph that doesn't actually exist on the graph, right? And on that one, it's flat. Okay, can calculate distance by adding all the sections together. Okay, now in Science 10, we only deal with really two different graphs. Okay, so it's easy to just kind of memorize what you can get from them. But what we want to have you be able to do by the time you're kind of into physics 20 is to not be memorizing what's on a graph. Okay, but to be able to look at a graph and go, oh, on this graph, the slope would represent this, just by looking at it. Okay, like we did with that thing with the share values. Okay, I look at that graph and I go, oh, well, the slope on that graph would be the value of shares per day. Okay, or if I was looking at the temperature in this room over the course of a day, I would say it's the change in temperature, per second or per hour or whatever it was. Okay, just being able to look at a graph and say, if I found the slope of that graph, this is what it would tell me. Okay, the reason we want you to be able to do that is if you go on to Chem 30, Physics 30, like in Physics 30, you're going to deal with more than 24 different types of graphs. There's no way you're going to be able to memorize all the stuff you can get from all 24 graphs. Okay, so it's better to be able to look at a graph and go, oh, all right, so that's what's on there. Here's what I can get from that. Okay, we got to be able to analyze a graph as opposed to memorize what's on it.
In physics 20, do you work with acceleration?
You're going to do that in Science 10 too. Oh, not with the graphs, no.
With the curves?
Yes, but not really in any more mathematical precision than we do here. Yeah, you'll do more of that in Physics 30. We can only teach so much because we have to follow what the math curriculum has done. Yeah, so that's why though. I mean, I know some people are like, why aren't we doing this yet? Well, because not everybody's learned that yet. You guys took Math 20 here first semester, but they don't take it till, yeah, so. All right, other things, we could calculate speed from this graph, okay? And that would just be, okay, total distance over total time. So really a graph is just a visual representation of the word problems you guys were doing on those V equals D over T worksheets. Okay, it'd be just as easy for me to have given you a graph of any one of those questions and asked you to calculate exactly the same things. Okay. All right. Questions on what we can get from the position versus time graph? Okay. Yeah, because it's on there, right? So that's, again, we're reading position and time. We could calculate total time. It would just be TF minus TI. We can write that. Right. Okay. So on this sheet here, we've got two graphs. One is a position versus time graph, and one is a velocity versus time graph that shouldn't have that line right there. Okay, so what do these two graphs have in common? Lines, okay. Yep. Okay, yeah, our measurement of distance is in meters, even though this one's not showing distance. Times both in seconds. Okay, there's only 5 seconds worth of data. What is the object doing in the first graph? Moving at a constant velocity in a forward direction. Okay, remember, it's not a curve, so it's not accelerating, right? The change in position, which is what this graph is showing, is constant. It goes up by the same amount every second. That means it's moving forwards at a constant velocity. What's this velocity versus time graph showing? The same thing, right? It is showing an object moving at a constant velocity for 5 seconds. Okay? These are the same object. Yes, that was my intent. Okay.
If you put a z-axis in the second graph, is that how you would show it?
You wouldn't need to.
Because well, the distance would be like up, right? Like the distance that it traveled on the first graph is
1,300. Graph starts at 100.
Oh, okay. Yeah. So then, if you wanted to demonstrate that same displacement,
I've never honestly thought about it. Yeah, I would say probably not. Even if you added a z-axis, it wouldn't. It would still. I'm not sure what that z-axis would be showing.
Well, because
Maybe.
It's
It's possible. But I'm going to show you how you calculate distance from that graph without making it three-dimensional.
okay.
Okay.
That'd be better.
All right.
I'm a little confused because the only line I see on the one graph is just staying at the same distance. So
Not distance.
no,
This is a velocity graph,
the left.
right? This graph is showing where the object's position, and that's changing, right? But this graph is showing the object's velocity, which is constant. And that's what gets confusing. Like if I throw this graph as a multiple choice question on a test, and I write as one of the distractors, object not moving, you wouldn't believe how many people pick it because they don't look carefully enough at the graph, right? It's an object traveling at a constant velocity. Sure, it's not changing, it's constant, but it's velocity, not position.
So in this first graph, why was it two lines?
Oh, I don't know. Someone just drew that to show that it would stop the time 5 seconds.
Oh,
That's not part of anything. No. It's just showing that the graph ends at 5 seconds. Yeah, this shouldn't be there. Yeah. Okay. So Jacob just pointed out here that the displacement in this graph is 1,300 meters because it starts at 100 and goes to 1,400. Okay. So could I calculate the slope of this line? Yes. Okay. I could go y equals m times x plus b because I know what b is. At time 0, b is 100. Okay. So m is going to equal y minus b over x. So that'll be 1,400 minus 100 over 5 seconds. Okay. And so that gives us 1,300 over 5, which is 265, right? Or 260, sorry. Okay, meters per second. Okay, V equals M. Everybody okay with that? Is that what that graph shows? Yeah, shows the same thing, right? This line is just above 250. Now I can calculate the distance from this graph, right? In fact, I didn't need to know this to do this. I just had to read off the graph that it was 260. Okay, so if I want to calculate how far this thing goes, can I use this formula? Yeah, essentially I'm just finding the area underneath this line, right? Base times height, because the base is time and the height is v. If I manipulate this for d, it's v times t, right? Everybody okay with that? Because technically I have to. I'm going to show you why in a minute. Okay? 265. Or 260. Sorry, 260. We've calculated it here. Yeah. All right, so this is an object traveling at a constant velocity. I can still use v equals d over t for that. What if I have that line instead? The object is accelerating because its velocity is going up, right? Acceleration is a change in velocity, okay? And that's what that line would be showing. So if I calculate the slope of that line, what am I calculating? The acceleration, because I'm calculating the rate at which the velocity changes. Okay? In this one, it was the rate at which the position changed. That's velocity. The rate at which the velocity changes is acceleration. Right? So if I calculate the slope of this line, let's just make some room to do that. Okay, so I'm going to use still m equals y minus b over x. Okay, I'm going to use, well, I kind of ran out of numbers here, but this is 450, 500, 550. Would be that top one there. So I'll just use 550 minus 100 over 7.5 seconds. Yeah. I can't believe I just did 550 minus 100 on my calculator. Yay. All right, so the acceleration is 60, but what are my units? No, meters per second are the units for velocity. I'm calculating the rate at which my velocity changes. What did I just divide? I divided meters per second by seconds, so that's meters per second per second. No, It's meters when I calculated the area here. Okay, so just to not confuse you here. Okay, so when I calculated this displacement, I went velocity, meters per second, times seconds. That made the seconds cancel and left me with meters. But when I calculated the slope of this line, I went meters per second divided by seconds. Right, which goes, right, when you divide fractions, you reciprocate and multiply. Okay, so that's the same as saying times 1 over seconds. That's meters. Seconds times seconds is meters per second is usually abbreviated as meters per second squared. Okay, meters per second is the rate at which the velocity is changing. It's changing by 60 meters per second every second. Okay, so the next second I'll be going 60 meters per second faster than the second before. That is an incredible rate of acceleration. To give you an idea, gravity is 9.81 meters per second squared. And gravity is a pretty good accelerator. Okay, 60 meters per second squared is like pulling your face back in the G-force thing. Okay, yeah, right. If you've ever seen those tests where they, they see how long it takes before they make somebody black out and their face like starts to peel back, yeah, okay, that would be kind of along those lines. Actually, it'd be a little less than that. Usually you black out around like 5 Gs. The human body can tolerate up to 20 as long as it's like for a short duration. Okay, but if you are subjected to more than 6 Gs for an extended period of time, it can start to be pretty harmful on your body. No, because we're sitting on it. We move at the same rate. Yeah, and it's constant. Okay, if you're on something that's constant, you don't notice it. Like if you're standing on a train, right? If you're on a train and you're walking on the train, it feels like you're walking normally, right? Because you and the train are moving at the same speed, right? Right. If I'm on the train and I jump, the train doesn't move under me. That would be bad, right? Agreed? Like because I'm attached to the train. If I jump, I still have the same speed as the train. Okay. Now it becomes different if you're outside the train, right? Because if I'm outside the train and I jump, then there's wind resistance, right? And then I might end up on a different part of the train. But inside the train, I don't have to worry about that. Okay. But yeah, so you don't notice it because we're moving it. Because yeah, otherwise, if I jumped on Earth, I would have to worry about the Earth spinning under me and ending up over there. That'd be bad because the Earth spins pretty fast. But because we're on it, we're spinning at the same rate. Okay, that's not what causes gravity. Gravity is caused by the Earth's mass. Yeah. All right, so does everyone kind of follow that? Where we got that meters per second from? Okay, now, next thing to try and calculate. On the last one here, if I wanted to calculate how far this thing had gone, I just took average velocity and multiplied it by time to get displacement, right? I used V equals D over T. But now the object is accelerating. What do I use for average velocity now? Its velocity isn't constant, is it? Okay, so Renaud? No, I can still use this formula. I just have to figure out what you're on the right track. That's something we'll do in physics 20. I like where your head was at though. Okay, I can still use this formula. If I accelerate from 100 to 550, do I have an average velocity somewhere in there? Okay.
So since like if like the first like spinning clockwise rotation, does that mean like maybe turning like counterclockwise would be harder than clockwise?
No, most of the planets in the solar system spin the same way. Venus being an exception, spins the other way, very, very slowly. Most of that just has to do with the way the solar system formed. Everything just kind of spun that way. Yeah, but everything spins at different rates. Like a day on Jupiter is 12 and a half hours, whereas on Earth it's 24, which because Jupiter's so big means that's a fast spin. Yeah.
I think I saw something this I know it's correct. I saw that planes flying opposite Earth's rotation are technically slower to get to their destination than flying with the Earth's rotation because they're so far out, gravity affects them less.
Not to any practical extent, no. We'll see. We'll see. So I'm just going to run through how we do this. Okay. Just let me do it here, Tanner, first. No, I don't need a tangent because I don't have any curve. Okay. So here's what I'm going to do. When I calculated the displacement for this line, I just calculated the area, right? I went base times height. How do I calculate the area of a triangle? Base times height over 2. Okay. Well, what's the height? What's the height measuring? Velocity. Okay, so if I go base, which is time, times height over 2, isn't that going to give me the average velocity? Shouldn't the average be right smack in the middle? Right? Okay, because this is the fastest, this is the slowest, this has got to be my average because I accelerated uniformly the whole way. Right? So my average has got to be right in the middle of my minimum and maximum values.
Couldn't you just go to the middle and do like m equals like y equals mx plus b just times like that?
Except that the slope won't tell me anything about distance. Remember, distance isn't on this graph, right? Again, there are ways that we don't do until physics 20 that will involve doing stuff like that. It's just because you haven't gone over some stuff in math 10 yet, we don't do it in science 10. I do like what you're thinking. You're thinking all right. Okay, there are other ways to do it, but we don't go over them in science 10. Let's take physics right away, and then you won't have to wait too long to find out how we do that. All right, so let's just work it out. Okay, so I'm going to go that the base of my triangle is 7.5. Okay, is 7.5 seconds, and my height of my triangle is 550. Okay, so I'm going to go base times height over 2 is really just doing this. Average velocity times time, right? This is finding my average velocity. The base of my triangle is in seconds. It's time. Right? So I take my 550 over 2, and I multiply that by 7.5 seconds. Okay, so yes, my average velocity was 225 because somebody had mentioned that. David, I think it was you. Okay, so I take my 225, multiply it by 7.5. Okay, so this thing is going to travel 1,687 meters while performing that acceleration. That's pretty far considering this only happens over 7.5 seconds. Okay, but I mean, it's accelerating at 60 meters per second. Like, it's going to be going pretty fast after 7.5 seconds. We will only deal with uniform acceleration, but yeah, acceleration can change. Like your car, for example, is not an example of uniform acceleration because your car has gears, right? In first gear, you have a much greater rate of acceleration than you do in fifth gear or sixth or however many gears your car has, because now they've got automatics that go up to like 10. Okay, it's like riding a bike. It's got that many gears. Okay, but each gear accelerates differently. Okay, and so it's not uniform. So you're right. Yes, there are lots of cases of non-uniform acceleration, but we don't deal with them in Science 10. Yeah. Okay, everybody following me there? All right, so the rest of it here is basically just talking about that. Okay, this graph here, again, it's a velocity versus time graph, and it's of a runner. Okay, so what is it showing this runner doing? Yeah, accelerating. This part's not uniform because it's a curve. Okay, and usually when you come out of the starting blocks, your acceleration isn't very uniform. Okay, there's a lot of slippage and things like that in the first few steps. But once you get your feet under you, okay, then you accelerate pretty uniformly until you hit your what? Yeah, you hit your top speed, and then you're pushing just as hard as you were while accelerating. It's just it's impossible for you to go any faster. Okay, so you travel at a constant speed until you cross the finish line, at which point you abruptly slow down and stop. Okay, that's what this is showing, right? It's showing a negative acceleration. Okay, all the way down to a velocity of 0. So this object stops at the beginning. All right. Yep. So he probably false started but got away with it. Yeah. Okay. He was already in motion. Okay, everybody all right with that? That would be also a sample question that I might give on an exam. I would give you a picture of a graph and not ask you to calculate, but ask you to tell me what's going on this graph? Okay, and so you would say on this graph, the object is accelerating for the first 5 seconds, then traveling at a constant velocity of about 8 meters per second, and then decelerating between 10 and 14 seconds, or accelerating to a stop at between 10 and 15 seconds. Okay, so you would describe it to me. Okay, and be as descriptive as possible. This would be accelerating positively, as opposed to just accelerating. This would be traveling at a constant velocity of 8 meters per second forward. This would be slowing down at a, for the next 4 seconds or whatever, okay? Something like that. Okay, right, so this is the stuff for the velocity versus time graph. So maybe draw this and write down what I have here. Yeah, give you a minute. Okay, this whole thing here that I'm going to circle in green, that's that whole meters per second is meters per second squared. Okay, so remember when I calculate the slope of this line, I'm dividing meters per second by seconds and getting the rate of acceleration in meters per second, which we always just write as meters per second squared because it's faster. Okay, so it's showing you the vertical value. What you can read off of a velocity versus time graph is velocity. Okay, at any instant. That's why it says instantaneous velocity. Okay, and it also the time. Okay, and then the area under the velocity versus time graph is the displacement. Okay, and we looked at how that was kind of base times height or base times height over 2, depending on which shape you have, whether your object's traveling at a constant velocity or traveling or accelerating. Okay, and it could get as crazy as I give you a graph that looks like this. Okay, so it'd be velocity in meters per second, time in seconds, and the graph does this. Okay, so I would have to calculate the total displacement of this. And again, if I put this on a multiple choice item, you know how many people would pick 0? A lot. Okay, it might be 0 because I didn't put any numbers on here, but okay, I would have several shapes because I have several different types of motion on this graph. Okay, I have this part where the object is accelerating, and I would have to calculate the displacement here by doing base times height over 2, average velocity. Okay, and then this one here is traveling at a constant velocity, so I could just go average velocity times time and know how far it goes here, and so on and so on. What would I have to remember about these 3 shapes? Right, they're negative. Yeah, the displacement there would be negative, so I'd have these positive values, these negative values, okay, and I have to put them together. Yes. Yes, it would. It would look oh man, I can't even draw that. It's going to be wacky. I'm trying to picture that in my head. You will not have to do that. That's a mess. But yes, it would have a lot of curves on it. Yes, it would have a lot of curves on it. Okay, it would have curves and then diagonal lines where it's traveling at a constant velocity and so on, right? So yeah. If I was asking you to draw a velocity versus time graph of a position, it wouldn't involve that, right? Like it would be, if this was, if I had a position versus time graph that looked like this, okay, like that, then I would say, okay, draw the velocity versus time graph, and you would go, okay, the velocity versus time graph is a constant velocity, and then not moving, and then a negative velocity. So like this, that's what it would look like. Yeah, except that this can't possibly happen because that's saying the object instantaneously changed speed, which is not possible. Okay, you can't instantaneously change speed. You have to. There has to be some acceleration. There has to be a force pushing the mass, and that has to take time. Well, there would be small little curves and stuff on there. Yep. Oh yeah. Lots of times. In fact, on the worksheet that you guys are going to do tomorrow, I've had people who drew me a graph that looked like this. They said the object traveled at 75 kilometers per hour, then it stopped and remained stationary for a while, and then traveled traveled back to the starting position at 75 kilometers per hour. Yeah, so they not only arrived back where they started, they arrived back at where they started when they started. That's what that graph says. So don't draw that graph tomorrow when you're working on graphing. Mr. Eden will be in here tomorrow with you. Okay?